Here is the conclusion of the mean value theorem that we have already seen. There is some point C between A and B at which the tangent is parallel to the secant. You have just seen that this statement holds for some functions but doesn't for some others. So what are conditions that will guarantee that the MVT conclusion holds? Let us investigate the examples from the problem you just solved. We have collected the successful functions, the ones for which the MVT conclusion holds, on the top row, and the failures on the bottom two rows. We will start by discussing why the functions in the middle row fail. Let us look at the first graph. For the first graph, we can shift the secant line to approach a point where it is tangent to our graph. But we find that the exact point that this would have happened is a point where the function is undefined. So there is no C. Next, let's look at the second graph in the middle row. It has a jump discontinuity at an endpoint. The secant line slants down, but all the tangent lines slant up. So there is no C. Because of the discontinuity, there is no relationship between the slope of the secant and the slope of the tangents. Similarly, for the rest of the graphs in this row, the reason that the MVT conclusion fails is a discontinuity, either at an endpoint or within the interval. Let's look at the bottom row now. Each of these two graphs is continuous but has a point within the interval where the derivative does not exist. In the first, there is a corner, and in the second, there is a cusp. You can check that the reason there is no tangent parallel to the secant is because of the point where the function is not differentiable. Let us now look at the successful functions. We can use the same method as before to find a point at which the tangent is parallel to the secant. We see that the first four graphs on this row have hump shapes at whose peaks the C's appear. On the other hand, the last function on this row is equal to the secant line. So at every point, the tangent is also equal to the secant line. In other words, every point within the interval is a C. What do all these graphs have in common? Well, all of these graphs are continuous and differentiable. Let's return to our question. What condition on a function will guarantee that the MVT conclusion holds? We already see that continuity and differentiability are conditions that will include all of our examples of successes and exclude all of our cases of failures. It turns out that continuity and differentiability are enough to guarantee success. So let us state the mean value theorem precisely. If a function x of t is continuous in the closed interval a to b and differentiable in the open interval a to b, Then there is some point C in the open interval a to b such that the average rate of change from a to b is equal to the instantaneous rate of change at C. Let's write this conclusion in terms of formula now rather than words. The average rate of change from A to B is equal to x of b minus x of a divided by b minus a. And the instantaneous rate of change at C is equal to x prime of C. Notice in the hypothesis, the function needs to be continuous on the closed interval, including the endpoints, but needs to be differentiable only on the open interval. So the derivative does not have to exist for the endpoints. Let us now do some exercises, and we will continue with some immediate consequences of the MVT.